Okay, so let's go ahead and pick up where we left off. I'm going to try not to like talk too fast or anything, but I do want to get through this part if we can. So in physical science, chemistry, physics, biology, you need to measure things, and we kind of talked about different units of measuring things and standards and things like that. But whenever you measure something, I should say, oftentimes when you measure something, you know the real value. Okay, so you know actually how accurate you are. Okay, so accuracy is a measure of what you came up with compared to the real value. Yeah, and the wind's kind of distracting back there, so if I start to, we should all just kind of go sideways so we could see, you could see me and you could see outside.
You could rearrange the bus for them.
That's a thought. I'm outside for class. So precision only comes into play if you've done the measurement several times. And actually, in this week's lab, you're going to do a measurement several times. Okay, so precision just is how you can get the same value each time you do it. And you're like, I'd always get the same value. Not necessarily. Okay, so it's how you read something. It's how in the case of Thursday's lab, the liquid dispenses out of your pipette. There's some kind of play in all of that. So precision is how reproducible your results are. And if you work or if you get results from like an analytical lab somewhere, they will tell you, with the analysis you asked for, they will tell you how they run with regard to accuracy, and they will tell you how they run with regard to precision. So it works pretty good if we kind of think of throwing darts at a bullseye. Of course, bullseye's where you're supposed to get. So the thing in the center would be the true value, okay? And the darts are like your stab to try to get the true value. So in this case, notice that it's not very accurate. Okay, so it's not, the average would not be in the bullseye. And it's kind of spread out. So it has poor accuracy, poor precision. Well, we could do this, where you're nice and tight, right? So you have high precision, you're very reproducible, but you're not in the bullseye. So your accuracy is not very good. Okay, and then we could do this, which you're very accurate, high accuracy, and your cluster is nice and tight. You can reproduce that result. I've toyed around with throwing darts. It's not easy. It's kind of fun, but it's not easy. I guess I would say that to me there's one more possibility. So if this is your bullseye, here's the center of the bullseye. Okay, so to me, if you want to hit it 5 times, you could have one here, and then you could have them spread out. So to me, in that case, you have poor precision. Oops, wrong core. Poor precision. But you have, to me, the average would be pretty darn good. You have high accuracy.
You would call that high accuracy?
Well,
If 1 is out of 5?
well, to me, a lot of times when you do 5 stabs at it, like this, 5 stabs at the bullseye, then you come up with an average, just a simple average. And to me, a simple average of that, just eyeballing it, would be the center. So, I don't know. I mean, your author didn't include it, but I think it's possible. But in that case, the poor precision might throw some flags up. Like, you're kind of all over the place. They just happen to average out to be accurate, so I don't know. It's a thought. So, accuracy is how close you are to the real value. And not always do you have a real value, but a lot of times we have a known value. So error is associated with accuracy. Uncertainty, and I'll kind of go like this. This is uncertainty. This is kind of my wiggle, my play. Uncertainty is kind of the spread of the values, is associated with precision. So error is how far away the value you measured is from the true value. And uncertainty is the interval, the kind of the spread of your uncertainty is the size of the interval that best represents the measured value. is best represented by the measure of the, it's the play. It's associated with precision. So oftentimes, and actually I think you're going to start playing around with this, there's ways of evaluating your work, statistically, or in this case, just a simple error. So absolute error means basically you take the difference of what, there's a couple ways of thinking about absolute error. But let's see, I'll put EXP for your experimental value minus, I'll put the theoretical value. And when I do that, the theoretical value is the actual. And experimental is what you got. Now it could be an average of what you got, but it's basically what you got. So it's just a difference. Usually we take, how do I say this? The sign matters. So it's not the absolute value of that, it is the sign. So this is to say, if your experimental is a little bit high, okay, then you'll get what, a positive difference there? If your experimental is a little bit low, you'll get a negative difference, and that is a sign associated with that. So while that's up there, well, I'll go ahead and do the next one. Relative error then looks like this. Relative error is you take experimental, EXP, minus theoretical, THEO, divided by theoretical. And to get parts per 100, usually I multiply that by 100%. Okay, that's just a little check how close you are. So not only, it's just basically the absolute error divided by the theoretical or actual value. So what, the closer you are to approaching 0 means you were right on the nose. If you get to 0 absolute error divided by your theoretical. Okay. Significant figures, if you want to put the word digit under figures, you can. Significant figures, significant digits, okay, are your friend. And you can count them in, you can count significant figures or significant digits in a number value, in a number associated with the measurement. Okay. So assuming that there's some uncertainty there. So we are going to count significant figures, significant digits. If in my grading, if you ever see sig figs, that's SIG, FIG, that means that something's not quite right there. I think I mentioned this the other day, that everything that you measure, there's uncertainty with it. Like, for instance, the length of this pen. I could come up with a length. And I would have to just kind of, we usually say estimate between gradations. We've been talking about gradations in here. Basically, my last gradation, I have to kind of estimate to the nearest, what we say, tenth of a gradation. And we'll talk about that in lab. But it's like a wiggle. It's like a plus or minus, right? So there's uncertainty in all measurements. And as we talk about this, ultimately rounding your calculations according to the number of significant figures you're allowed, we're going to kind of propagate through the problem the correct uncertainty to the person who reads your answer. That's the way I look at it. And it's true. So what I'm going to show you about rounding ultimately is something that's done worldwide in the scientific community. Okay. Not to mention probably the commerce too, you know, people buying and selling things. So significant figures or significant digits look like this. If at the top you want to go ahead and put uncertain digit, put a question mark there, that's how I show it. So for instance, if I measure this device, this pen thing, and if I come up with 6.25 inches, like this is telling you, here in the 100ths place, that digit 5 in the 100ths place, that is I'll put a question mark, that is uncertain. This is all this is saying. This is saying as you write from left to right, the rightmost digit, if there is uncertainty, is uncertain. So I kind of do it this way. I'll put a question mark over the 5, and I'll put a, let's see, how do I want to do this? I'll put a check over the 2 in the tens place, and I'll put a check over the 6 in the ones place. That's to say, I know for sure it's 6 inches. I know for sure it's 2/10. But the 500th, and maybe as you've learned it, a lot of times we just kind of go plus or minus 0.01 inches. That 0.05, I don't know, it might be a 0.06, might be a 0.04. Okay? So that's where we're going with all that. Now, there's uncertainty in everything measured, all measured quantities, unless you get that measured quantity by counting. So for instance, I would count, there's 8 people in this room. Okay? Now, it's not like 8.8 people plus or minus 1. Well, think anyway. Okay? It's not 8.5 people. Anything you get by literally counting items is what we call one of 2 types of exact numbers. There's no uncertainty, no question mark. The other sort of exact number, and we're going to run into this when we work problems, is by definition. Here, the other day, a really good one, there's a couple good ones, but for instance, the other day we talked about the metric system, and I could say 1 km is equal to blank meters. What number do I put in there? 1,000, yep, very good. So 1 kilometer is equal to 1,000 meters. That is by definition. That's within the metric system by definition. There's no question mark there. We ran into, do you guys remember the answer to this one? I think you do. 1 milliliter is equal to blank centimeters cubed. They're exactly equal, 1, exactly. That's another by definition. Okay. So by definitions, when we get going, if you're using a by definition sort of relationship in your calculation, then you don't have to round. It brings no uncertainty. All right. So how do we count those significant figures? Well, here's the rule. So let's just say you're given a number and it's a measured quantity. There's uncertainty, and we need to count significant figures. First off, if the digit is not a 0, put a little check there because it's significant. The zeros are the hard thing, and I'll give an example of this next one. If it's a 0, but it's nested between 2 non-zero digits, you better count it. So an example of the first one, I just give 1, 2, 3. We count all of those. So we have, what, 3 sig figs? An example of rule number 2 would look like this. Let's say I have 1,023. So according to rule number 1, I count the 1, the 2, and the 3. And according to rule number 2, I count that 0. So I'm at what, 4? 4 sig figs. Here's one. Trailing zeros after the decimal place. Now, so think of the decimal place, and then think of trailing zeros to the right of that. They are significant. So an example of that looks like this. 1, 2, 3, decimal 0, 0, 0. That's a decimal there. So the first rule says I count the 1, 2, and 3. This rule says that I need to count these trailing zeros after the decimal. So how many sig figs I got there? I'm counting 6. Oh, did you have a question?
Trailing meaning 2 or more?
Trailing, no, it could just be 1. It could be, that's a good question. I could do another one. 1, 2, 3.0, and then I would have 4 sig figs. 1 or more. Yep. And a good way, and I'll use this as an example to think of it, is we could kind of look at that last zero and say it's plus or minus that tens place. So for instance, this would be kind of the tolerance or the uncertainty plus or minus, plus or minus 0.1, right? This would be plus or minus 0.001. They're two different measuring devices. Looking at it another way, and I can see that I just now can put my checks instead of, go ahead.
So, yeah, that last, so the 123.000, that last check, would that be a significant figure, or is that the uncertain?
It's both. It's a significant figure, and so kind of, I just now thought of that. I used the convention incorrectly, but I'm going to go ahead and put a question mark there. It's both. It's where the uncertainty lies, because it's the rightmost digit, and it's significant because it's a trailing zero after decimal. Sorry about
Really,
that.
only zero that's not trailing, that would be to the left, would be insignificant.
Right, we're getting to
Every other
that.
zero
Yeah.
counts.
Because you're saying if it's 0.0123,
Yeah, I'm
Yeah.
saying everything else is.
actually
significant.
that's right here. Leading zeros, that was a leading zero.
There you go.
Yep, are not significant. Yeah. I think there might be one little catch to that pad rule coming up, so.
Wait.
Yeah, so very good. Sounds like, are we all on the same page? This, a good example here would be 0.0123. And we count the 1, we count the 2, and we count the 3 because of the first rule. And this rule says that leading zeros, and leading zeros are just what I call placeholders. Have you ever heard placeholders? Okay. They're just trying to give magnitude to the rest of the number. So in that case, this is not significant. And I go back to what you said back here. Remember, even though I put a check here, that's actually also, it's significant and it's my uncertain digit. So. Now, I say they're not significant, but you got to have them. So there's a difference. It's not like you can throw them out because it shows magnitude. And I'll show you, I'll try to convince you why it doesn't change the relative uncertainty. I have an example to kind of hopefully talk you through it. Then we have one other example of zeros. And this might be where it kind of, it gets a little, okay. In this case, if I were to write down the number 1, 2, 3, 0, 0, 0, right? That was 123,000, right? Notice, okay, so you guys tell me, where's the decimal?
Zero.
The decimal is after the zeros. And this is my own convention. I'm going to go ahead and put the decimal there, and I'm going to put some little dots around it. Those dots around it means that I went ahead and put it there. Actually, there's a name for this. This is called implied decimal. We all know it's there, okay, but no one put it there. It's implied that it's there. So this says trailing zeros before an implied decimal. That's what this is. Are not significant.
What if the decimal point was there and had zero after it?
Let's do that example. That's a good point. So what if we had 1, 2, 3, 0, 0, 0, decimal 0?
All those be significant?
Mm-hmm.
Wait, time out. They're significant because of why?
Well, I look at it this
Oh, wait,
way.
because they always are significant.
Well, I look at it this way. I say 1, 2, and 3 are significant because of the first rule. I'd say this 0 is significant because of,
Trailing zeros after the decimal point.
right, yep, because the third rule, okay? And then I would say those 3 zeros are significant because they're between 2 significant digits. Mhm.
So when you're giving, say, like, the results of an experiment, you're required to have so many significant figures in that answer?
Mhm.
Okay, I was just confused why that makes
Yep.
sense.
Yep.
So
Yep.
you have to make sure to include
Yep.
certain-
So kind of what you're getting to is what y'all, some of you probably really remember is your teacher said you have to round according to, and it's going to be fewest number of significant figures if you're multiplying or dividing. And so that's why it's important to be able to count significant figures in all the terms that you're using in your calculation. Is that what you said?
Yeah, that's what I was trying to figure out.
Yep, yep. Yeah, so this is how you count them. And then here in a minute, we're going to show why that's, no pun intended, significant. All right. Any other questions about that? So I'll give you a minute. Do you guys have these? Write down how many sig figs each one of these are. Or do you already have them right now? They are.
You want the slide itself?
Yeah, it looks like you have the slide. So go ahead and, for instance, say how many sig figs each of these are. And then I'm gonna have you hold up your fingers, so how many significant figures there are. Okay, get your fingers ready and your toes if you need them. Okay. So how many sig figs in this first one? I'm liking it. Very good. How about this one? I'm liking it too. Very good. How about this one? Yep. Very good.
2 or 3?
3.
3.
Nice.
Because that's a trailing 0.
Mm-hmm. Trailing 0. Anybody else want to take a stab at explaining why this is 3?
Because I thought trailing.
Because the
The
uncertainty.
trailing 0 after the decimal.
Because it's uncertain, so that makes it significant.
It could have been a 2.51 rounded.
So, and uncertain digits are still significant figures, right?
Yes.
Okay, so
Oh, well,
that's.
there you, I can deal with that.
Oh, good. Thank you. Thank you. Yes. Uncertain digits are still significant. You get 1 though. You can't have 2. Yep. Very good. Good, good. How about this one? Fingers. Fingers, please. And why did you think 4, Emily?
Because you have now trailing digits, and you have 2 of them, so, well, I guess one's still insignificant, so it would be 5.
5. Sounds like you convinced yourself. Very
Because
good.
then the one sandwiched between 2 significant, or 1 significant and 1 uncertain, so that would make it
That's
significant.
right. That's right.
Okay.
Only this last 0 is uncertain. This one is
Sandwich.
hardcore. Yeah.
Got it.
Yep. Okay, last one. How many sig figs?
There we go.
Ah, you guys are like 50-50. If I was balancing my checkbook right now, I'd be like, there's 2. Why is there 2?
Because all the zeros are on the left for 1. They're not significant or uncertain because neither one really applies.
Right, and then
They're place values.
they're placeholders, yep,
Holders.
yep. This is the one place where these are not significant. So there's only 2. Okay? So here's where I get to kind of show you why all of this is a little bit. Now, if this is like, TMI, that's fine, just kind of go with it. To me, one of the things I said, if these are all pounds, like 2.5 pounds, 2.50 pounds, 2.500 pounds, you know that you paid a lot of money for this little for the balance that could spit you back to the nearest 0.001 pounds. Okay, so we're increasing money. But I'm going to try to show you why those trailing zeros after the decimal are significant. Here we go. So how does this go? The absolute uncertainty, the play, we'll look at it that way, of the first one is 0.1. The play of the next one is 0.01. The play of the other one is 0.001. So to get relative uncertainty, we're going to take that wiggle, that uncertainty, and we're going to divide it by the real value, which is 2.5, 2.50, and 2.500. So here we go. So if you divide 0.1 by the actual value, 2.5, you get 1 in 25 parts. That's the relative uncertainty. If you divide if you divide 0.01 by, again, 2.50 now in this case, you get 1 in 250 parts. That's the relative uncertainty. And of course, then the last one, if you divide 0.001 by 2.500, you get 1 in 2,500 parts. So not only does that last scale cost the most, but that last scale will give you wiggle room 1 in 2,500 parts as it's weighing. So these trailing zeros after the decimal make a difference with regard to relative uncertainty. I'm going to do a similar thing now for those leading zeros. So here we go. I'm going to try to kind of walk you through a proof why those leading zeros, like 0.0123, that decimal, or excuse me, not decimal, but that 0 does not count. Try to show you how that works. And like the slide says, they're important. Every once in a while, have students try to just, if they're not significant, try to throw them out. But they are important because they give magnitude of 10. But here's how that proof would look. So in this case, if I were to ask you how many sig figs, hold up fingers, how many sig figs we got in each one of these quantities? 2 sig figs in everything. And I'm not going to do it here, but if you were to go ahead and write out plus or minus, and then write out the tolerance or the uncertainty, go ahead and do what we did just a little bit ago. Take that uncertainty, divide it by that number. You're going to get 1 in 25 parts for each one of those ratios. So your relative uncertainty is constant for all of these. So anyway, it is. So one more thing I want to kind of talk about before we head into how do you round numbers is this idea of ambiguity. I love that word, ambiguity. Ambiguous. Some of you know ambiguous. So this is that implied decimal here. So you guys would tell me that the decimal's after the last 0, but it's implied. So we don't know if we have 2 sig figs. We don't know if that first 0, that's where the uncertainty begins. That gives us 3 sig figs. If we are uncertain to the nearest tens, that gives us 4 sig figs. We're uncertain to clear out to the nearest ones. That would give us 5 sig figs. We do not know. So, so this is saying that, let's see. Okay. So what this is saying is that if you were to take the, what was it, 1, 2, 3, 0, 0, 0, and you were to go ahead and put the decimal, I guess it's probably 1, 2, 3, 0, 0. If you were to go ahead and put the decimal there, okay, let's see, implied. I was trying to think of what's the opposite of an implied decimal. You put the decimal. It's no longer implied. You actually put it there. The convention is that that means that this 0 is significant if the decimal's there. Sometimes students, If you need to relay your answer to 5 sig figs in this case, you could put the decimal there and you'd be done.
So this one would be that there is nothing that is, what's the word, insignificant? What's the one that has a little wiggle room?
Uncertainty.
So this one, because it is certainly significant, then there's not any.
This one actually, the uncertainty always lies in the last digit, so this
it's
would be,
still there,
yeah, plus or minus 1. Yep.
even with that.
Yep.
Okay.
Mm-hmm. Yep. Okay. So, this would have 5 sig figs.
But without the decimal point, would it be 2?
Yes.
Well, if there was a 0 after, it would still be 5 significant figures, correct? Would that be still at 6? Because then it would be, yep. Okay.
Yep, you answered your own question. Yep, if there's a decimal and a 0, then now it's 6 significant figures. Yep. So, cool. Well, you probably, and I'm not going to take time to go over scientific notation, but I'm hoping that you're already familiar with scientific notation. I think Petrucci actually has in his appendix a little bit about that if you don't. But in scientific notation, just to kind of remind you, we call this the coefficient. Actually, we call something else the coefficient later on in chemistry, but this is the coefficient. Okay, and I call this the exponent part, this part over here, times 10 to the 4th. So actually, each one of these, if you move the decimal place over 4 places, you're going to come up with the same number. It's 32,000. These are all 32,000, packed up in scientific notation. Now, the point is, if you have a number that's in scientific notation, you pick off significant figures from the coefficient and call it good. So that's why 32,000 packed up is 3.2 times 10 to the 4th. There's 2 significant figures. If in the coefficient you add a trailing 0 after the decimal, now you have 3 significant figures. Okay, 2 trailing zeros, you have 4. 3 trailing zeros, you have 5. See how that works? So as we get going, rounding your number to the number of significant figures, rounding your answer to the number of significant figures that you're allowed, sometimes you have to go with scientific notation. Okay. All right. So yeah, if you have any questions about scientific notation as we go, let me know. Keep me posted. Okay. I know this says some people use the convention that when a number represented in measured quantity is written ambiguously, it's assumed that it represents the fewest number of significant figures. I think that's probably everybody. So 32,000, for instance, without any decimal, you're looking at 2 significant figures. That's all that means. Okay, so 2 significant figures there. All right, drum roll. So in chemistry, we do a lot of multiplying and dividing. We do a lot of multiplying and dividing. We don't do much of this. And this is adding and subtracting. Okay, and how you round your answer, it depends on if you're adding and subtracting, which we don't do much of, or if you're multiplying and dividing, which we do much more of. I'm going to kind of show you why this is, but in a nutshell, this is the rule. I'm going to show you why it is. The rule is that if you have a string of things you're adding and subtracting, what you do is you put it in your calculator, and your calculator spits back a number. Then you have to take one last look at that and round it correctly. And in order to round it correctly, you revisit each term that you added and subtracted. Okay? And I know this says you count decimal places. Well, some numbers don't have decimal places, so I'll kind of talk you through that. But it's the fewest number of decimal places in all the terms that you round your answer to. And I'll go ahead and tell you, it says decimal places or tens places. Let's see, you can report the answer to the same number of decimal places or tens places, fewest. Okay. So here we go. I'm going to show you why this is. So for instance, now we've seen different glassware in the lab that some is like, can be really precise and hopefully have better accuracy. And sometimes gradations like in a beaker are really loose, okay, widespread, and you'll have, your precision probably won't be as good and your accuracy will be a little bit less. So here we have somebody trying to add these two volumes. So here we go. We know to add them, we line them up on the decimal. You know, if we weren't going to use our calculator, we'd line them up on the decimal and kind of add each column. So in this case, you see that red hot number 2, that's my uncertain digit. And I'm going to add to it this volume. And that red hot 4 in the tenths place is where the uncertainty lies in that volume measurement. So of course what we know is that now we go ahead and add them. And notice in this case, this 2 made this 2 red hot, and this 4 made this 6 red hot. Red hot meaning uncertain. And so kind of the way I look at it is that kind of 4 sandwiched between the 6 and the 2, it turned red hot too. So our calculator spit back 29.642, but the last 3 numbers, the .642, is all uncertain. And remember we said you can only have one uncertain number. So that's why you're going to see the answer is actually truncated there. We keep the 6, and hopefully we kind of remember how to round. We keep the 6, and since the digit after it is a 4, if it was a 5, we would have rounded up. Since it's a 4, we just lop everything off. So the correct number to report would be 26.4 milliliters. Excuse me, you know what I mean, 29.6 milliliters, final answer. Okay, so that's adding, and be the same thing for subtracting. And if we go back and look at the problem, this is what I mean by counting decimals. If I just were going to count decimals, I usually put a 3 there, 3 decimals. I put a 1 there, 1 decimal. And why am I counting decimals? Because I'm adding. So how many decimals am I allowed? 1, that's it. And that's what we do. So, okay. So switching gears, multiplying, and dividing, it's a little bit different. And again, I'm going to show you why this is. But this is the rule that maybe most of us remember, because we do a lot more of this in chemistry. It's similar to adding and subtracting, but what I do is I let my calculator go ahead and multiply and divide all the numbers I ever want to multiply and divide. And I take one more look at it after I get my calculator display. I count fewest sig figs, and that's what I round. I surround my answer to sig figs, and that's it. That's it. Okay. So this is why this happens. So in this case, we have lengths, a couple of lengths measured using different devices. We have a rectangle, and we want the area of a rectangle, so we need to multiply length times width. And so notice we have a plus or minus the 1/100ths in this one. So actually here in a minute you're going to see question mark over the 4, and here we have a question mark over the 1 in the tens place there. So here we go. If you're like me, I have to concentrate. How do you long multiply, or, you know. So, does it take the first one? Yeah. So I have 2 lines here, if you remember how this works. This first line here is to take this 1 and multiply it through everything at the top. And then what I do is take this 1 in the 1's place, and I multiply it again, but I slide everything over. Let's multiply. My point is, and again, we kind of line up the numbers, and we bring them down, and we keep our red hotness. Okay? So notice that actually the red hot starts here with this 1 plus 2 is 3. Then what you do, I don't know if you remember because I barely remember, but the last thing you need to do is put the decimal place, and it's going to be actually from the right 3 places because I had 3 decimals up there. I know it's been a while for me. So the decimal goes there, and I have a red hot number there. So in this case, we're going to keep only one red hot number. In this case now, since we have a digit of 5 after where we want to round, we need to round up, right? So the answer is going to be 14 centimeters squared. That's it. And while I have this here, let me show you simply, if I had these two numbers, what I would do is I would count sig figs. I got what, 4 here, I got 2 here, and I go with the fewest. What's the fewest then? 2. So I'm allowed 2 digits. I need to round to 2 significant figures. So that's how that works. All right? Okay. So on one slide are both of the rules that we talked about. If you're adding or subtracting, you have to count fewest decimals or tens places. And if you're multiplying or dividing, you count sig figs. And then don't forget, so we talked about 2 types of exact numbers, those by counting and those by definition. Those aren't, you don't have to, don't round according to them at all. They're like neutral. They're like Switzerland. So these will be due, and I'm going to kind of show you these. But let me know if you run into any snags, but you should have answers to those 3 problems under doc sharing. Let me know if you can't find them. So I've got these ready to send for anybody who wants or needs them. And this is what they look like. So 19's red, so the answer is under doc sharing. Express these to 4 significant figures. In some cases, you'll need to round them. Okay. In some cases, I'll just give you a hint. I bet you guys are maybe kind of already see through this, but look at C there. You want 4 significant figures. So I want the uncertainty to begin at the hundreds place. To me, you're going to have to pack that up in scientific notation and show 4 sig figs in the coefficient part. Okay. I think. I think you guys will do okay with the next one. And here's the next one. Now this one's still okay because I don't like it when you mix adding and subtracting with multiplying and dividing. It just drives me nuts. But these are okay. Should be okay for that. And then this one, it mixes, for instance, C and D. Okay, watch out. Remember the order of operation is to fix your numerator and your numerator and denominator. I want to say fix, I mean simplify. So in this case, you have to add these together first. And if I was working this problem, I would add these together and I would actually write a number. And then I would put this number down here and do a division. When we add, we're going to go with fewest decimals. So I'm looking at 1 decimal here. Okay? And then divide by that. That's probably what I would do for homework. And it might not exactly match your answer in the back of the book, but that's fine. And these I would... And the next one, it takes it up even a bigger notch. So we have just multiplication, division in the first one, first 2. The third one is addition, so we're going to round according to decimals. And then the 4th one, D, kind of takes it up a notch. Now, these are almost like brain teasers. I will warn you, especially D. We kind of talked to one student about it. If this drives you nuts, don't let it drive you nuts. Just push on through it, okay? And significant figures are one of those things that if you haven't been exposed to them much, you kind of pick it up as it goes, as you go, excuse me. With that said, when I grade your homework and when I, of course, grade your unit exams, I'm going to be looking for a correct rounding. So, any questions about that? And this is the last one. So you have a few problems to do. It'll be fun. Okay? Oh, and since this is Monday, Wednesday, so honestly, I've had students really take me up on it. If you come Wednesday, and I always have to collect the homework at the beginning of the period, but if you come Wednesday and you still have questions about your homework, you can, after class, we can all just kind of go over and meet at the library, and we can talk about it. So you don't have to turn them in right when class starts. You can go over, ask questions, and then hand them in after the study session or at the study session. Does that make sense?
Mm-hmm. So this is your Wednesday?
So this will be due Wednesday, yep. Okay, and I'll send it out in email. Okay, let me know if you have any questions in between.